This is part 6 of my lecture on parametric tests for comparing means, and I'm going to be talking about comparing two paired samples. In comparing paired samples, we're given samples with a matching relationship between two populations. I'll explain what that means in a moment. The available data is two samples of paired measurements taken from these populations. And what we want to do is to test whether there is any difference between the means of each sample. The statistical test that we're going to use is the paired t-test, sometimes known as the matched t-test. So the paired t-test or matched t-test requires two samples, and inevitably there must be the same number in each sample because they're paired, as we'll see in a moment. They must be paired by something that corresponding measurements have in common. Usually this is because they come from the same subject. In medicine, very often because they come from the same patient. So for example, it could be something like the patient weight before and after treatment. So if we have a weight before and a weight after treatment, each weight belongs to a particular patient. So there's a pairing between the pre and post weight because each pair belongs to a different patient. That's what we mean by pairing or matching in this context. What we do is take the difference between pairs of measurements. That has the advantage of cancelling out any systematic difference between subjects. So it's only the change in weight that matters. So a heavy patient who gains a kilogram or a light patient who gains a kilogram have the same change in weight. That way, by pairing up a before and after on every patient, it doesn't matter that some of our patients are light to start with and some are heavy to start with. It's the change in a paired measurement that matters. Then we test the difference in weight, for example, to see if it's compatible with 0. And the way we do that is by using the one sample t-test on the difference, because once we've taken the difference between each pair of measurements, we've only got one sample left, namely the difference. And the difference should be approximately normally distributed for this to work. So the individual weights don't need to be normally distributed, but the difference in weights should be normally distributed. The paired t-test calculation has a number of stages to it. Let's suppose that we have pairs of data. Let's call it xi1 and xi2, the I representing the number 1, 2, 3, 4, and 1 and 2 representing sample 1 and sample 2. So in each sample there are n measurements, so we have n pairs of measurements. The mean of sample 1 we'll call ms1 for the mean of sample 1, and the mean of sample 2 is ms2. That means the difference is xi1 minus xi2, the difference between the measurement from sample 1 and the measurement from sample 2. I'll call d for the difference, and there's one of these for each pair of measurements, because I'll call it di. What we have to do is work out the mean difference. The mean difference is actually the same thing as the difference of the means, so we can calculate it as the mean of sample 1 minus the mean of sample 2. Then we have to calculate the variance of the differences. This is a little bit more complicated because we have to take the difference di minus the mean difference md and square it, add them all up and divide by the number of measurements n, and that gives us the variance of the difference. That's exactly the same formula as we used early on for the variance, except this time I'm doing the variance of the d rather than the variance of the x's. Then the standard deviation of those differences is determined just by taking the square root of that variance. Now you might believe that you can calculate the standard deviation of the differences from the standard deviation of each sample, but in fact you can't. You have to calculate all the differences and then take the standard deviation in this way. Once you've got the standard deviation, we need the standard error of the mean, which as always is the standard deviation divided by root n minus 1, because we've estimated the standard deviation from the measurements. We don't know it from the population, so we have a root n minus 1 rather than the root n. Once we've got all that, we have a t statistic as our test statistic, very much as before. MD, the mean difference, divided by the standard error of the mean. Don't worry that that calculation is rather complicated. Excel can do it using its data analysis tool. So what does it all mean? Well, MD is the mean difference between the pairs, as we've seen, and the standard error of the mean is an estimate of the precision of that mean difference. We determined it by estimating from the sample standard deviation. That's why we've got a root n-1 in the denominator. The test statistic t then is that mean difference as a fraction of the standard error of the mean. It is the difference as a fraction of how precise we think that measurement is. But as before, because we've estimated this standard error of the mean from the sample standard deviation rather than from the known population, it's not going to be normally distributed, but it follows the t distribution with n-1 degrees of freedom. N here is the number of pairs of measurements, the number in each sample. So the recipe for the paired t-test is first take the difference between the pairs of measurements, then calculate the mean and standard deviation of those differences, estimate the standard error of the mean as the standard deviation of the differences divided by root n-1. Divide the mean difference by the standard error of the mean to give the test statistic t. Then we look up the critical value of t from the table of the t distribution with number of degrees of freedom equal to the number of pairs minus 1. And if t is greater than the critical value we've looked up, then we can reject the null hypothesis. So let's take a hypothetical example relating to some vitamin pills and weight. And our question might be, does taking vitamin pills alter your weight? So the hypotheses are that vitamin pills alter your weight, and the null hypothesis is therefore vitamin pills do not alter your weight. So is that a one-tailed test or a two-tailed test? What do you think? We've done quite a few one-tailed tests up to now, but this one is definitely two-tailed because we said vitamin pills alter your weight. We didn't say they make you heavier or lighter. Either direction would be significant as far as we're concerned. If your weight increases or your weight decreases after taking vitamin pills, that's something that would be of interest with this hypothesis. We don't specify a direction, so it's a two-tailed test. Here's some hypothetical data from 8 subjects who were weighed before and after a course of vitamins. And we can see there the weight in kilograms of the 8 subjects before and after. So the statistical test that we're going to use is certainly because the data are quantitative, we can use a parametric test. Here the data are definitely paired because we have the same patient before and after, so they're paired in measurements for every patient. So we're going to use the paired t-test. So graphically we can represent the data like this. Here we're showing weight vertically and a measurement for each patient before and after joined by a line, showing that some of the lines went up a bit, some of them went slightly down, and some hardly changed. So there is a mixture of gaining weight and losing weight, and I wonder whether looking at that you can see whether on the whole patients tend to gain weight or lose weight or no change at all. I think from this graph you can see that the change is rather small, but maybe there is just a slight trend in the upwards direction. But the great spread of weights between patients means that if we didn't pair them up, you would say there was no difference between the before and the after. But by pairing them, we've overcome the significant difference between the lightest and the heaviest patient, and just looking at change of weight enables us to see has there been a significant change. That's the significance of pairing and using the paired t-test. Another way of displaying it is like this. We've put the weight after on the vertical axis and the weight before on the horizontal axis. So the solid line at 45 degrees, the line of identity, would be where weight before and weight after were exactly equal. And by putting a dot for every patient corresponding to weight before and weight after, you can see that actually most of them are slightly above the line, which means that the weight after was a little bit more than the weight before. So that's another way of displaying our data. To do the calculation, we first of all start by taking the difference in weight. So the first subject was 65 kilograms before and 69 after. That's a gain of 4. The next was 79 before and 78 after, which is a decrease of 1. So we have a difference of -1, and so on. We calculate the differences for every patient. If we add up all those differences, taking account of the plus and minus signs, we get a total of 24 kilograms. So the average, the mean weight difference, 24 divided by the number of differences, the number of pairs, is 8. So that 24 over 8 is 3 kilograms. So on average there was a weight gain of 3 kilograms. Now to calculate the deviation from the mean, 4 is 1 above the mean of 3, -1 is -4 from the mean of 3. In other words, if the average is 3 gain and this patient lost 1, they are 4 compared with the mean, 4 below, -4. 5 is 2 above the mean, and so on. So the deviation from the mean is the weight difference minus 3 kilograms. Then we have to square those deviations in order to calculate the variance. 1 squared is 1, -4 squared is 16, 2 squared is 4, and so on. If we add up all the squared deviations from the mean difference, we get a total of 82. The variance of the difference is the mean squared difference, 82 divided by 8, because there were 8 subjects. 82 divided by 8 is 10.3. That's in units of kilograms squared, and if we take the square root of that, we get the standard deviation of the difference. Root 10.3 is 3.2. So the standard deviation of our difference is 3.2 kilograms. So we have to estimate the standard error of the mean, and as usual we take the standard deviation 3.2 divided by root n minus 1. N was 8, so n minus 1 is 7, which is 1.2 kilograms. Notice we're using n minus 1 because we're estimating rather than knowing the true value for the population. So we have the formula for t as the mean difference md divided by the standard error of the mean. The mean difference is 3, the standard error of the mean is 1.2, 3 over 1.2 is 2.5. So we have a t of 2.5 with 7 degrees of freedom, because there are 8 subjects, 8 pairs, and the degrees of freedom is n minus 1. So here's our table of the t distribution. If we look across the row for 7 degrees of freedom, we find that for a two-tailed test, remember we're doing a two-tailed test this time, for a p-value of 0.05 to reach a significance of 0.05, we need a t of 2.365. So from that t distribution with 7 degrees of freedom, for our significance level of 0.05 with a two-tailed test, the critical t-value will be 2.365. If you remember, our t-value was 2.5, so it has exceeded the critical value. Our result is significant with a p less than 0.05. So we can reject the null hypothesis with 95% confidence. So we can conclude that vitamin pills did affect the subject's weight in this case. Now, it was a two-tailed test, so it could have increased or decreased, but our difference between the mean was positive, so on the whole there was an increase in weight. So not only is it a significant difference, but we can say it was a significant increase in weight. But because we did a two-tailed test, a decrease in weight would have been equally significant according to this criteria. So that's how we can use a paired t-test to see the difference between pairs of values, which often happens in nuclear medicine or in medicine in general, because we're often dealing with patients and paired results are quite common.